Hello everybody. What I would like to do in this pre-lecture is focus on stoichiometry, and we'll talk about some other concepts of how we do stoichiometry. We'll get to limiting reagent at the end. Okay, so we've talked a little bit already about the importance of mole ratio, and let's focus on a particular reaction as we go through some stoichiometry problems. So a reaction you are probably familiar with. This is the combustion of propane. And propane has the formula C3H8. All right, so you see it here using to fill up this hot air balloon with gas molecules, and we'll talk about what those are in just a minute. So let's focus on, for pretty much the rest of this pre-lecture, this reaction of propane, combustion reaction of propane. So let's scroll down here and see what this looks like. So propane, combustion reaction, is going to react with the oxygen in air to produce carbon dioxide and water. And that's assuming complete combustion. You probably know that if combustion is not complete, you're going to get some carbon monoxide. If it reacts with the nitrogen gas in air, so if it's not a pure oxygen environment, you're going to get some reactions between the propane and nitrogen. Probably get some nitrogen oxide compounds and whatnot. But let's not worry about that. Let's assume complete combustion. Okay, so you do need a balanced equation to do stoichiometry. We've talked about that a little bit. All right. You might want to double check this is balanced, and you might, to practice balancing equations, just write out on a separate sheet of paper C3H8 plus O2 goes to CO2 plus water, and then see if you get the same balanced equation. All right. This reaction, as you can see in the image above with the burner on the hot air balloon, also produces heat and light. Or we're getting ahead of ourselves here, but we'd call this an exothermic reaction. You've probably heard that term before. More on that later. So let's just work a problem. You need a balanced equation. You need to know about mole ratio. That is the key concept. So this image here is really kind of showing the coefficients as a molecule ratio. 1 molecule of propane with every 5 molecules of O2 to produce 3 molecules of CO2 and 4 molecules of water. But we're going to scale that up much more than just a few molecules. We're going to scale it way up, and we're going to scale it up into the mole region. And so we're going to read those coefficients as a ratio of 1 mole of propane, since there's a coefficient of 1, 5 moles of O2, so they're going to react in a 1 to 5 ratio, and then for the products, 3 moles of CO2 and 4 moles of water. All right, so it's important that you know how to read those coefficients as a ratio of how those species react and are produced in terms of moles. So let's just work a problem. So 400 grams of propane is burned in excess oxygen. Okay, so typically if you were doing this, say you have a propane grill, all right, there's going to be plenty of oxygen, so we don't have to worry about the oxygen. How many moles, and let's stop at moles here. We'll talk about grams later. How many moles of CO2 will be produced? Okay, so here's your typical stoichiometry problem. You're starting with a certain amount of reactant. We want to know how much product is produced. All right. Now, what's the key? Mole ratio. So we don't have moles of propane. So we can't yet go to moles of CO2. We need moles of propane because we know the mole ratio, right? For every 5 moles, that's oxygen. For every 1 mole of propane that reacts, we're going to produce 3 moles of carbon dioxide. But we don't know how many moles of propane that we have. So that's the first thing that we need to do. So if we can get from grams of propane, C3H8, to moles of C3H8. Then this is where we can do stoichiometry. All right, this is the key concept for stoichiometry. We can apply the mole ratio to get to moles of anything else in that equation. Anything. We could go to moles of O2, find out how much oxygen we needed for that reaction. We could find out how much CO2 is produced, which is what we're going to do. We could also figure out how much water would be produced. This is the key right there, and we should then be able to get to moles of CO2. All right, so do we know how to go from grams to moles? I hope so. What do we need? I've asked that question way too many times. Molar mass. So, 400 grams. Calculate the molar mass of propane. I hope I did that right. I did that right before I started this pre-lecture. We could estimate, but I'm going to use a few more sig figs. 3 times 12 for carbon, that's 36, plus 8 for the hydrogens, that's 44. And a few more sig figs, I have 44.094 grams of propane. Watch your conversion factor so that you have grams in the right place so it cancels. Grams in the numerator of 400 grams cancels with grams in the denominator. Now we have moles of propane, which is what we want. Okay, now that we have moles of propane, we can go to moles of anything else in that equation. Okay, so don't think it has to be product. It could be O2, it could be another reactant, or it could be one of the two products. And in fact, what always tends to throw students off, we can even go backwards. I could give you the amount of product and say how much reactant would you have to react to produce that much product. So we can go either direction in the reaction. Okay, so now let's do some stoichiometry. We now have moles of propane. This is where the mole ratio comes in. Coefficient of 3 in front of CO2, coefficient of 1 in front of propane. 3 moles of CO2 is produced for every 1 mole of propane. That's all there is to it. Just take the coefficients. There's your mole ratio. Again, you have to watch your units so that moles propane cancel, and you're left with moles of CO2. See what we get here? I did not put those numbers correctly into my calculator. Let's see. Okay, so 27.21 moles of CO2. All right, that's all there is to it. Now, I've quite often asked you to take a look at that and see, is that about right? Is that about the right amount? Now, I'm going to estimate here and make our life a little bit easier. So instead of 44 grams per mole, let's just round that down to 40. Okay? So estimation is a powerful tool, and sometimes you'll simplify things. So I'm going to say, well, the molar mass of propane is about 40. So 400 divided by 40 is how many moles of propane? 10. So we have about 10. Actually, it's going to be a little less because we're dividing by more than 40. But for estimation purposes, about 10 moles of propane. The mole ratio is 3 to 1, so we're going to get 3 times as much CO2, or 30 moles. Okay, so make sure you can start thinking through things like this. So 10 moles of propane, estimated. 3 moles of CO2 for every 1 mole of propane. We're going to get 3 times as much, 30 moles. We calculated 27. We're in the right ballpark. That looks good. All right, last thing with this problem. I said let's stop at moles. But what would we do if we were asked for grams of CO2? Does that cause any problems? Shouldn't. We know how to go from moles to grams, correct? Yeah. What do we need? Molar mass. You get the idea. So you have to read the problem. Not every stoichiometry problem is the same. Some stoichiometry problems in the chapter we're on, you'll start with grams, and you'll go all the way to grams, say, of product. Some you might start with moles and end with moles. So you have to read the problem carefully and see what you're starting with, where you're ending. But remember, if we want to go from one thing in the equation to something else, we need to compare them in terms of moles. So we do need to get to moles so then we can get to moles of something else. Why don't we do this calculation here that I mentioned about going to grams, because then I'm going to talk next about something called percent yield. So let's just finish this and say, what if I had asked for grams of CO2? We need the molar mass. CO2 is about 44.01 grams per mole. Notice that the molar mass of CO2 happens to be about the same as the molar mass of propane. Okay, 1 mole of CO2 cancels with moles of CO2 in the numerator, multiply by the molar mass. And this, maybe I should have chosen this example because the molar masses are about the same. Oh, the mole ratio is not the same, so that's going to work out okay. All right, let's try this again. 27.21, and then we're going to multiply by 44.01. Okay, and to 4 sig figs, I get about 1,198 grams of CO2. Okay. All right. So again, read the problem carefully. Look at what you want to get to. You know, some people will call these problems GMMG problems, gram to moles to grams. I hesitate to do that because it's not always grams to moles to gram. It depends on what I ask you to solve for. In the original problem, you actually stopped at moles. Okay, so watch out for that. All right, next concept. It's actually a fairly simple concept. Percent yield. So different reactions are going to have different percent yields. Some higher, some lower. It could be because of impurities in the sample. It could be there are side reactions, and that you get multiple products. The reaction branches off in different ways. You could lose some product on some of the glassware you're using or whatever. So your percent yield will not be 100%. Now, combustion reactions, the percent yield is going to be quite high. But let's say you actually run this reaction in the laboratory. You react 400 grams of propane, and you collect the CO2 gas that's produced, all right, and you determine that, okay, so again, you're doing this in the laboratory, that 1,141 grams of CO2 is produced. Okay, so this is actually measured. All right, this is not calculated. You would actually, in the laboratory, collect your product, figure out how much you got. So we call this the actual yield. All right, and that makes sense. That's what we actually get in the reaction. Now, since this is a problem I'm having you work, I'm going to tell you the actual yield. We're not in the laboratory right now. I hope I'm not in the laboratory. Nope, I'm at home right now. I just checked. So I'm going to have to give you the actual yield. Well, what is this yield up here that we already calculated? That is what we call the theoretical yield. Theoretical. Okay, and that makes sense. Theory. In theory, what could we get? If everything went perfectly, how much CO2 could we get? Okay, so in effect, that's the 100% yield. If everything went perfectly, we'd get 1,198 grams of CO2. Well, we did not get 1,198 grams of CO2. Maybe we produced some carbon monoxide. Maybe, some nitrogen and oxygen and air combined to produce some nitrogen oxides. Who knows? But we did not get, in theory, what we could possibly have gotten. And in general, that's the case with reactions. Okay? So, percent yield. What we really need is a fraction, part divided by the whole, multiply by 100 to get a percentage. That is a percent. Part divided by the whole. All right? So our part, our smaller number, is our actual yield. Our larger number, our whole amount, is the theoretical yield. All right. That's a fraction. Multiply by 100 to get a percentage. That's all there is to it for percent yield. So we take the 1,141 grams. We do have to make sure our two yields are in the same units. For example, if we had stopped here at 27.21 moles, and then the problem said you produced 1,141 grams of CO2, you would have to make sure you were in the same units for each one, whether it was grams or moles, either way. 1,198 grams, multiply by 100. And I calculate 95.24% yield. All right, and as you'd expect for a combustion reaction, our percent yield is going to be very high. All right, probably even higher than that, but I was just making up some numbers as we go along. All right, so remember, when you do a stoichiometry calculation, you are always calculating the theoretical yield. In theory, what is the maximum amount that we can get? In reality, your actual yield will be less. That you would measure in the laboratory. In a problem, it will be given, and then you calculate the percent yield. Okay, last thing for the pre-lecture. Let's talk a little bit about limiting reagent. All right, and let me go back to the propane example. Okay, so let's write out a reaction of propane. All right, so we already, let's say that I'm going to change this now. So a lot of the problems you'll work will say so much of this reactant was reacted with excess. So in effect, what that problem is doing is it's telling you which reactant is going to run out first. All right? But what if I give you the amounts of both reactants? What if I give you the amounts of both reactants? All right? So say we're going to react 400 grams of propane, like we did up above, and let's say we react it with 600 grams of O2. Okay? And let's just stop at moles. How many moles of CO2 are produced? Let's just keep it simple, because we know once we get moles, we can get to grams. All right, so limiting reagent. What that means is which reactant runs out first and limits how much product you can get. The other reactant will be in excess. So one of them is going to run out first. Once it's gone, reaction stops. That's it. So how do we know which one's going to run out first? Now you might first look at this and say, well, we have less propane in terms of mass. It must run out first. Oh, not necessarily. Be careful. You can't necessarily say that because they're reacting not in a gram ratio, but in a mole ratio. Okay? So again, we need to work with moles, not grams. So be careful. So there are different ways to figure out the limiting reagent. I've taught chemistry for, oh gosh, almost 25 years now. So the way, and I've taught it different ways. I've taught limiting reagent different ways over the years, but I've settled on this way, and I think it is, and I talked to Jen, talked to your SI. She'll probably confirm this maybe, but this is the way I think is the easiest way to do this. We are going to do two separate calculations. So the first one, we're going to do the calculation for propane and ignore that O2 even exists for the calculation. We're going to assume, say, O2 is in excess, like we did up above. All right. So 400 grams of propane, assume O2 is in excess. How many moles of CO2 would we get if all the propane reacts? Now, we've already done this calculation. So let's quickly write this one back in. So I didn't want to take too much time for this pre-lecture. I believe the molar mass was 44.094 grams propane, and the mole ratio is 3 moles of CO2 for 1 mole of propane. And I believe we got 27.21. Is that correct? I can hear you. Tell me if it's correct. I'm going to scroll back up. 27.21. So this is the calculation that we've already done. Okay? But again, I just wanted to save some time. So this problem again would state 400 grams of propane is reacted with 600 grams of oxygen, O2. How many moles of CO2 can be produced? Well, what we've done in this first calculation is say, well, if all of the propane reacts, we can get 27.21 moles of CO2. Now we're going to turn our attention to O2. So the second calculation, we're going to ignore propane, or we can say, well, let's assume propane's in excess. Let's see how much CO2 we could get if all of the oxygen were to react. So we're going to do the same calculation. We can't go from grams of O2 to moles, directly to moles of CO2. Where do we have to get to? We have to get to moles of O2, then we can apply the mole ratio. So we compare things in a reaction in terms of moles. All right? So 1 mole of O2, 32 grams. Okay. The molar mass of oxygen atoms is very, very close to 16. So we'll call that 32. All right. So that gets us to moles of O2. Now we can get to moles of anything else in that equation. We want to get to moles of CO2. 3 moles of CO2 for every 5 moles of O2. And let's see what we get here. All right, so limiting reagent. Basically, we do two identical We do two stoichiometry calculations in the same manner, one for each reactant. Okay? One for each reactant. All right? One of these calculations is correct, one is not. So which is correct? Because we certainly can't get both amounts. All right? So the question is, again, limiting. Look at that word. Okay? One of the reactants is going to run out first and limit how much product we can get. So the correct answer is the smaller amount. O2 is going to run out first, and the reaction stops there at 11.25 moles of product. All right? We will never get up to 27.21. Okay? So O2 is what we call our limiting, I already wrote limiting here, limiting reagent or limiting reactant. Okay? And what would we call propane? That would be our excess reactant. All right? There's going to be propane left over. All right? We didn't have enough, they weren't reacted in the correct stoichiometric ratio. O2 runs out first, limits the amount of product. And that is our correct answer. So I think I'm going to stop there. Oh, I want to say a couple more things. Again, it turned out that the substance that we had more mass of, O2, turned out to be our limiting reagent. So don't look at that. Okay? You could definitely steer yourself in the wrong direction. And I thought there was one other thing that I was going to say. I guess the last thing, and this maybe, I don't think this is what I wanted to talk about. But again, make sure you notice you might be asked to go to grams of CO2. Not a big deal. We know how to go from moles to grams, molar mass. Okay, my voice is about to wear out. I guess that means I should stop. I hope this helps you understand stoichiometry a little bit better, and we will practice some more of these problems in class. All right, I will see you soon. Take care.